would like to introduce Cesare Gallarti, CEO and founder of RISC-V Security.
Thank you, Tim. Good morning, everyone. Thank you for joining us. Let's speak a bit about security mixed criticality systems and what they really are. So these are typically embedded or deeply embedded applications where you have real-time applications typically implemented via a microcontroller, MCUs, or in any case, single core deterministic kind of systems that now are more and more merged with Linux-capable hardware. And most of the time, this happens in the very same SoC, in the very same component. This opens up a whole new set of challenges in terms of securing these systems. And so the mixed criticality is really coming from one side, the need for safety critical application. You see a picture of an autonomous vehicle here. That's a classical example. There might be lives at stake. There might be very expensive assets involved in this kind of applications, from automotive to aerospace, defense, transportation, healthcare. At the same time, all the benefits of Linux or rich operating systems in general, including the memory management unit and the virtual memory separation that comes with it, are required. And so what do we do when we have multiple trusted workloads or applications on the same untrusted platform to the end? So Linux is the one that you will hear me referring the most, but the whole idea is that there is a number of thick software, system-level software, whether you want to call them operating system, where we define them as thick hypervisors. There are variations on the team, but there are many, many lines of code and a very extensive code base in the end that exposes the system as a whole at this point, because it's just one, to vulnerabilities. And so sharing the same core or sharing multiple cores in between the safety critical part of the system and the less critical one that runs this enormous code bases is probably not a good idea. And so whether system the designer relies on some level of separation through hypervisor or traditional hypervisor technology or similar approaches, there are a couple of things that will not be addressed by that kind of approach. So one, I'm talking about the RISC-V in particular architecture, which is new and it's open source and everyone seems to be interested, but the very same concept apply to more established platforms out there. And so one thing that you want to keep in mind is the highest level of privilege in that very system or in the set of cores that comprise that SoC. In the RISC-V, or this is called the M mode or machine mode. And the software that we are trying to standardize within the RISC-V Foundation is something that we call SBI, System Binary Interface. But the whole idea is that when you have one core, the core can only be in one of the privilege modes. And if you share that privilege mode in between trusted and untrusted, then you definitely run into troubles. The other aspect to consider is memory, whether it's an L0, L1, L2, depending on the system, but anything that ends up in cache, can be extracted from cache. And so if you have common, let's call it a cache pool, it depends really from the configuration of the system, but generally speaking, if you have cache memory that can be addressed by a core, well, once the core accesses the data, it takes a lot to secure eventually and make absolutely sure that the data will not end up in the less critical part. So another very interesting aspect that is emerging in terms of requirement is this concept of zero trust. And what zero trust really means is you have to assume that these very complex systems at this point embed a number of parts, and typically these are really software libraries or nested software libraries, so vendors that give you libraries that include libraries that are using, that are built on top of other libraries, and in the end, no one really knows where the software is coming and what is the threat model that is exposed to, whether there are nation states involved, where there is any other kind of intentional or unintentional vulnerability included. It's very simple. So if you look at drivers, if you're familiar with any kind of embedded Linux application from home gateways, just to give an example, to similar applications, there's a number of drivers that come from lower level hardware, network part of the SoC, Wi-Fi, connectivity, crypto libraries, you name it, right? So these drivers are typically run in the Linux world in kernel mode. And so to the point, the bullet point that I just showed above, they are definitely running in that highest privilege mode that eventually exposes the system as a whole to vulnerability. Now, as I said before, it's really not about who's better and who's more reliable, I'm safer than you or anything like that. It's just about size. In the end, it boils down to be about size. And so we will see in a second, but there is a statistical, well understood statistical correlation in between how many lines of code or how many brain power went into a piece of software and how many defects or bugs or vulnerabilities that then eventually become attack vectors we should expect into it. And so let's see what does it mean. Again, let me start by saying I'm a big fan of Linux. Within X5, our company, we rely on Linux completely for development. In fact, we use Linux in all our laptops as well. So this is not about saying anything bad about Linux. It's just about sharing some data, some facts, right? So what you see here is something that you can check yourself. It's an open source tool. As everything really we do or we work with, you can go online and point this utility to any version of Linux. In particular, this is the Linux kernel, okay? So it's the minimum denominator, common minimum denominator of the systems. Systems are, in fact, way bigger. So what this utility gives you, it's a count of number of lines of code. And then it's broken down in terms of what programming languages and so forth. But the whole idea is that if you point to Linux 4.18, just to pick one, you get 17 million lines of code. Now, if you just apply a little bit of logic and math, I did my research, you can do your own, but the best ratio defects per number of lines of code that I could find, it's something that point about 10, 15, 50 per 1,000 lines of code, something better than Microsoft was able to develop with some additional work was something that get a little bit better. But I think the best one I could find out there is something that I think was used then for the shuttle project. I might be wrong with that, but in the end boils down to be a number, single-digit number of defects per 1,000 lines of code, or even better, 0.1 per 1,000, which means one defect every 10,000 lines of code. Well, it sounds like very, very teeny tiny chance there's something that can go wrong, but then if you just run the math, and so 17 million lines of code times 10 to the minus 4, that's 1,700 problems just waiting to happen. Now, not all these problems need to be that serious, like privilege escalation or any kind of buffer overflow or misuse of shared memory that we are familiar with in terms of attacking Linux kernel. But the point is that size does matter, and this level of complexity, and again, this is just the kernel, which per se doesn't really run any application. You have to add millions of lines of code on top of this to get any embedded Linux system to work. It's simply not something that you can blindly trust in a safety critical application. Very good. So let's speak a little bit now about RISC-V and what the RISC-V ISA provides in terms of security primitives. So now that we have seen what kind of problems what kind of troubles we are getting in when we mix criticality system in one single SoC, let's see what we can do. And so this is the RISC-V approach to it. These are standard basic primitives that are part of the ISA instruction set architecture. So this is nothing vendor specific. You should assume, you can assume you will find all of this in any RISC-V implementation that you will run into. So on the left side, we have something which is called privilege modes. Let's build up a little bit the slide here. So these are exposed in terms of control and status registers, nothing really special here. In RISC-V, we have the machine mode, M, that's the highest level of privilege, is always present. If there's no M mode, that's not a RISC-V core. It's that simple. And then we have the supervisor mode. Supervisor mode is what supports the MMU, memory management unit, and therefore is what is intended to be used in Linux-capable systems. That's the virtual memory access. There is one more level, which is called H for hypervisor, that has been defined as we speak. Perhaps next week at the RISC-V Summit in San Jose, we will learn more about the status. There's a lot of work, a lot of excitement, but as of now, there's no standardized version yet. And then there is the user mode. User mode is very interesting. It's the fourth mode, is the lowest level of privilege, is what is used by user-land applications in a Linux deployment, but interestingly enough, can be in fact just mixed with the M mode. And so if you look at the second line with the number 2, when you mix M and U, so cores that don't necessarily run Linux, or they have it, but you don't use it, then you have a very deterministic and secure system where the memory management unit and all the things that go with it is not part of your attack surface. And so trust execution environments, or enclaves in the jargon of Linux, live in that kind of world. Just a note, don't forget that systems work with interrupts. Interrupts are asynchronous, and they bring in additional execution threads that typically completely bypass any kind of separation. So unless there is something very specific in the system, all the interrupts, all the hardware, all the drivers definitely bring the processor up in the highest level of privilege, which is a major concern in terms of security. Very good. So let's look on the right side of the slide. As a complement to the privilege modes, RISC-V provides something called physical memory protection, or PMP. You might be familiar with other platforms where this is called MPU, memory protection unit. It's the same concept. You can define a set of registers. They are typically memory mapped in other systems. In the case of RISC-V, they are in fact controlled through the standard ISA through some privilege registers, CSRs again. And so you can have a mix of this kind of configurations, whether you define adjacent memory spaces via the starting address and the end address, which is called top of range, or where you rely on more sophisticated technologies that actually give you a little bit more, can pack better information in those registers, called natural line power of 2. There is a mix, there are variations. It's a little bit complex to set up, way easier compared to other platforms that I'm familiar with. But the point is that this is hardware enforced. When you define physical memory protections, those adjacent memory spaces, blocks, regions, cannot be accessed by the core. It's that simple. There's no way to bypass it. It's as solid as it gets because it's super simple, and there's really nothing that can go wrong if not a bad implementation of the core, which eventually would be caught early stages in the development of the product from formal verifications. Okay, so in the case of RISC-V, we have also the policies associated with that. So you can define these ranges, say, hey, this core has access or not, but then you can mix, read, write, and execute policies there, which makes up for very interesting deployment scenarios. Again, the trust execution environments, or the enclaves, rely on this kind of low-level, super strong separation, and so the PMP, or physical memory protection capability, is managed by the trust execution environment. Okay, so I think this is the core slides. So let's see how we apply those very building blocks to an actual real case of the PolarFire SoC, Microchip PolarFire SoC FPGA, and see how we can address the problems of mixed criticality systems. What you see in this slide is an actual Microchip component. Tim will tell you a little bit more in a few minutes about this. but this is as real as it gets. In fact, we have a live demo planned for the next few minutes, where you can see on the right side 4 cores. This is one single SoC, okay? So this is one component. On the right side, there are a number, in this case 4 cores, capable of running Linux or any other operating system that can address, they can drive the memory management unit. So you see the 4 modes that I explained with different colors, and you see Linux living in those 4 cores. In this case, it's an SMT, symmetrical. You can have 3 cores running Linux and a 4th one running something else. That's okay. But the only idea is that on the right side, you have the less critical part of the system. And it's not less critical because we don't care about security. It's just because, what I said in the very first slide, we cannot really trust just the code base. It's just too extensive. And there are so many components and dependencies throughout the supply chain that definitely would not lead a designer to put an autonomous vehicle, for instance, just in the hands of that kind of framework. On the left side, we have a 5th core. And this is a core as all the others. It's simplified or hardened, if you want, in a sense that it doesn't have the S mode, so it doesn't have the the MMU, so there's no virtual memory. You can look at the one on the left side as an MCU, powered up MCU, because it has 64 bits, it's the same kind of core, same kind of performance. It just doesn't have the floating point unit and the S mode. And so that's where your safe hags should be. And just to elaborate a little bit more, the black part of the schema of the chart here is the hardware itself. And as you can see, it's a RISC-V hardware that provides that U mode. It's the final U in that IMACAU. So we rely on that hardware, which is the physical memory protection building blocks, to realize a separation enforced by the hardware, but defined via software, for 4 different domains. We call them zones. You can call them enclaves, containers. The terminology is up to what you want to use. But the whole idea is that these 4 safe areas, or 8, or whatever you need in your design, are completely isolated from the big block on the right side. And so they are isolated among themselves, but also with regard to the less trusted part of the system. There is no shared memory, no shared resources, and in fact, these 4 zones live in a world of themselves, but connect, interact, exchange messages over a secure channel. Secure means that there is no shared memory, right? So it cannot be attacked, which is based on IPC. In this case, IPC is inter-processor communication. Don't forget, these are 5 processors inside the same SoC. And so here is what we get. We get multiple equally secure zones or enclaves that can map any piece of the RAM, ROM, I/O. Interrupt handlers as well are executed in the safe context of the user mode of these zones. This is enforced by the hardware, as I said. So unless the hardware is flawed, there's really no way to beat this. But it's defined via software, which is really unique and innovative and gives you all the flexibility you want. Basically, you can redefine the security posture of your system anytime you reflash this device. And because of the safe boot capabilities of this hardware, that's enforced throughout the running of the system. And extremely lightweight. The red thin layer of software you see on the left side, which is the MultiZone Security nano-kernel or separation kernel, by design, it's extremely small. It's less than 2 kilobytes. So this is less than 2 kilobytes of software that you have to trust your system with, okay? Compared to hundreds of kilobytes or megabytes of other systems, that makes the whole story. Very good. So as of now, this is the only commercial Linux enclave or trusted execution environment for RISC-V. As I said, you'll see in the next slide how easy it is to configure and deploy it. It comes in the form of a toolchain extension, so no coding required. And you don't need to rewrite your software. So this is, again, very innovative of the Microchip solution. Okay, so let's see how it works a bit. So what you see on the left side is the configuration file that supports the configuration that I just put in the previous slide. Just very quickly, for the first zone, and you'll see a live demo in a second, what we do, what the designer of the system does, in a flat file, defines these policies. For zone 1, we have two regions. One is for the code, the text segment. The other one is for the data. It stays somewhere in memory, some address, some size. Notice the policy. Read and execute for the first one. That's the text segment. That's the program. And read write for the second one. That's flat. That's now. So read write. Now, zone 2 is not different except for the addresses. So here is where the separation is and how it's really defined. So nothing really to say about this. Different regions, same kind of structure. Now, zone 3 is a little bit more interesting. You will see in the demo, we connect a UART, which is some sort of local hardware. And so in this case, we map some physical resource at the UART port. Zone 4, same kind of thing, but it's driving some LEDs on the Microchip board, and so it needs to access some different hardware. As you can see, I'm really mapping the whole system here bit by bit and assigning to the zones statically, so that it cannot be messed up with runtime, so that the system behaves as desired. Now, the final part that I'm building right now is the big block on the right side. That's the untrusted world where Linux or those SMP or AMP to that extent, rich operating systems live. And so in this case, it's 4 cores. So as you can see, heart 1, 2, 3, 4. Heart is the terminology that RISC-V uses for the hardware threads, right? In this case, 1 thread per core, so these are really 4 cores. And so what we do here, we start blacklisting rather than whitelisting all the resources that we don't want the unsafe part of the system to be able to address or deal with. And so this, if you pay attention, are exactly the parts that are used by the safe ones. And so this is a blacklist. Notice the policy. Dash, dash, dash means no read, no write, no execute. Basically, no nothing. You just get an exception. And, well, in the end, you need to give access to everything else as in every other blacklist. So if you can write this file, and you can see it's super easy, you can secure a system. And that's the end of the story. How it works is that you have individual 4, in this case, for the 4 zones, pieces of code, really byte streams. The code might not even run. Doesn't matter, because the safety critical aspect of the system is enforced by the preemptive MultiZone kernel, and that's the first option you see on the left, that tick time 1 millisecond. It means that if any of these zones keeps the core busy for more than 1 millisecond, it will just go on with the next ones. So you cannot create denial of service in any way. So you create those 4 executables that can be compiled, linked completely separately, no cross-references. You can use different programming languages, different versions of C. It doesn't matter how they come up with. What it matters is that you use this toolchain extension that puts them together, injects the right version of that 2 kilobytes of nanokernel, and then merges these policies. It's then signed, and it ends up in the secure boot firmware of the PolarFire SoC. Is that simple? And so this is really the presentation. What I would like to do now is to give you a live demo. So what I have here on my left of my desk is a prototype, a working prototype of the PolarFire SoC. It's a big board, really. Tim will tell you more about the actual silicon that is coming out very soon. What we do, and what you will see me doing, is this is a Linux system, so I use an SSH session, which is secure, obviously, by definition, to connect to enclave number 1. And then I will interact with the dumb terminal bare metal application that is running in the terminal 1. And I'll show you the physical memory protection settings and what it looks like. And then I do exactly the same from a second terminal that connects at this point to a second enclave. These connections happen through Linux, okay? So it's super easy for Linux to interact. And we don't have time for that, but if you come and join us at the RISC-V Summit next week, you will see also how we do the very same, but connecting to a completely different piece of hardware, which is the UART on the system. Very good. Sorry about this. It is a time when we go through the live demo, and please add your questions if you have any there. And I will address them. We will address them very soon. Okay. So let's connect to the system. Very good. So what I have here is an SSH connection to the Linux board. And so the password gives me access to Linux, and what I have here is my Linux session. So let me show you something here. So if I look at the devices available here, you will see that this Linux system, in fact, let me redo it so that it's better aligned, has a device that has 4 instances, and this is it's a read-write block character standard Linux device driver, but it exposes access to those 4 zones, to those 4 enclaves. And so what I'm going to do now is to open a screen to the first one. This is standard Linux way of doing things. Very good. And let me refresh the screen. Here we are. So again, I'm coming in from Linux. This is a Linux user mode application that in a very seamless way with the Linux world is now interacting with some protected piece of the system, protected environment, that is in fact running in a completely different core with a completely different piece of the cache allocated to it in the most secure possible way. And so just to give you a sense, we have coded a few test options to check the security of the system. And in particular, this PMP shows you the policy. And so for this zone, those are the 2 policies that we entered from the configuration file. These are burned into the flash. They cannot be changed. And if I try to do load and stores, which is access to memory, read and write, for instance, I'll read with a load from my first address assigned to the first segment, which, unless I'm wrong, is this number. Okay, the load succeeds, and I get the value 97.7. Okay, not that impressive. Now, let's do a load at an address to which I don't have access, just randomly. And so here is what happens. I get a load access fault. So in a nutshell, this gives you a sense of what it looks like. It doesn't matter what code is there. It doesn't matter where it's coming from. I don't trust anything about that. The most it can do, intentionally or unintentionally, is to raise an exception in the core. The exception is handled, and the system keeps going. Now, let's do a little bit of more sophisticated use case. Let's open a second session to Linux, which is identical to the first one. Very good. And so this is the password. Okay, I'm in. So I do exactly the same, but this time I connect to a different zone. Good. Aha. So what you see here, and I can go on and on and on, right? So this is just to give you a sense. So what you see here now is 2 Linux user mode applications, unprotected, unprivileged, eventually exposed, that are interacting in a secure way to a secure environment that is running 2 completely separated applications. Now, if I show you the policies, you will see that the policies are different. You see the addresses are different. And so if from zone 1, I try to load, let's change the address, 800, 7000. It succeeds because it's my first address in this range. But if I do the same from the second one here, and I enter the right value, it fails with an exception. So I can go on and on, but we don't have time, unfortunately, and I do want to leave some time for Tim and for your questions. Just want you to show you how the system eventually works as a whole, and it is done through secure messaging. Secure messaging is an exception handling mechanism across the cores. And so if I want to send them, the messages are what basically keep the system working. It's equivalent of APIs if you want, but in a secure world where there's no shared memory, right? So APIs rely on heap or stack. In this case, it's done through exception handling. So if I send a message to zone 2 on the right, and I say Cesare, here is what happens. On the right side, you saw the message coming in. And at the same time, I can eventually send a message one and say Microchip, and it shows up on the other side. Now, messages are anything the system designer wants them to be. Typically, they kind of mimic the behavior of APIs, but these are done at a very high level, and so typically just move some protected information back and forth this environment. And with that theme, I think I'm going to go back to our PowerPoint, bring it full screen, and let you comment on the PolarFire slide.
Okay, thank you very much. Nice demo. So PolarFire SoC is a single monolithic piece of silicon with a hardened RISC-V processor subsystem in it. You can see this block diagram here. Anything that's not in that low-power PolarFire FPGA architecture block is an ASIC implementation of a 5-core RISC-V subsystem. We'll be making some additional product announcements next week about PolarFire SoC at the RISC-V Summit, so I do recommend everybody to show up there. But you know, it is an SoC FPGA, and it has kind of like security built in from the ground up. We're well known in the security space, and the Hex5 MultiZone Security layer running on this just extends security from our silicon to our, your user space applications. We have a deterministic L2 memory subsystem that's built into this chip. It's kind of unique. You can configure the L2 memory subsystem to be a cache, or you could configure it to be a local memory, or it could be configured to be a scratchpad memory, which can be used to share messages across all 5 cores coherently. And with those 3 combinations, you can create kind of very flexible and unique systems for mixed criticality systems. You can, run Linux on 3 cores in some trusted execution environment on a 4th core. Okay, and you can use the PMPs and multi-zones to logically isolate these systems from each other. So you can provide determinism and security in a trusted execution environment, and you can, use all the wonderful things that Linux brings to the table in and wall that off in its own secure enclave. So we're pretty excited about this, and as I mentioned earlier, we'll be making announcements next week. If you can go to the next slide. Since multi-zone is really, kind of a software security layer, you really need secure hardware first before you can enable that software security layer. And Microchip is a pretty solid supplier into the aerospace and defense industry. We're actually #1, okay? And a lot of that has to do with, our security capabilities. And PolarFire SoC has been built on top of PolarFire FPGA. And we do, womb to tomb type of security through manufacturing and through deployment of your systems, where we have all the necessary features and IP to make and enable security in your systems. Now, since we're adding an SoC, we have to add SoC-like security to PolarFire to create PolarFire SoC. So we have secure boot built in. We actually have 2 versions of that. One that we will roll out to the broad market in an open source way. It is side channel resistant, okay, to side channel attacks. So it's very secure. And there's another method that you can roll your own. There's a method to protect some of your boot code in a puff protected non-volatile memory, okay? And you can design your own secure boot scheme to meet your own unique application requirements. This is kind of unique in the industry. Most, processors in the market deliver a secure boot solution, and here it is. We offer you too. And since we're security conscious, we chose an architecture that is naturally Spectre and meltdown immune. I mean, it's a very simple thing to do. You don't choose an out-of-order machine, which are exploited by Spectre and meltdown. So the CPUs in PolarFire SoC are 5-stage in-order machines, okay? And as Cesare mentioned, we have physical memory protection built in, and, we also do error correction on all memories. We'll do single bit correction and double bit detection. And when you get a double bit error in a memory in the processor subsystem, you have to consider, where that error occurred and whether or not your system becomes unstable at that point in time. It could be a stack, or it could be a variable that gets corrupted. And so we route error signals from the processor subsystem into the FPGA fabric. Okay, and then you can set your own policies through logic design in the FPGA fabric to respond to these error signals. You can count the frequency of single bit corrections, or you can count, if you get a double bit, detection, you possibly could reset the processor subsystem if you want to. So we give you the capability and the tools to tailor your response to an event based on your own system requirements. Okay. Next slide. So definitely want to thank you for attending this webinar. This is the 5th Microchip Fields Up webinar. As a reminder, we're running these webinars every 2 weeks, barring any kind of holiday, international holiday or national holiday here in the US. And we record these and we post them up on the web so you can review them at your leisure. Any questions about MultiZone, please reach out to Cesare. Any questions about PolarFire SoC, there's an email address you can reach out to there. And, come visit us next week at the RISC-V Summit in San Jose if you are in the area. I did have a question, Cesare, and that is, I think MultiZone is somewhat instruction set architecture agnostic. We've been talking about RISC-V here today, but I think you have solutions for processors that don't implement trust zone. Is that correct?
That's correct. And so the other platform that we offer a solution for is a subset of the ARM cores. And in particular, we have a solution that will be announced in a few months, sometimes in Q1, that targets M3, M4, and most importantly, M7 ARM cores. It's the same philosophy. You can look at this as a standalone core MCU kind of approach, and that's what those M3, M4, and M7 are for. Or you can look at solutions like the PolarFire SoC, where that MCU or a couple of those MCUs are in fact part of a larger SoC that includes some Cortex-A with trust. Same logic, same concept, same super easy to use, which is great news in this case, and same resiliency. And most importantly, I think we offer this on some of the Atmel Microchip cores as well. People who are interested, I think, will see the announcement and the first in a general availability, really, hopefully, sometimes in end of February at the Embedded World show in Germany.
Okay, so this is, we don't have any questions. As I mentioned earlier, if you want to ask questions privately, there's a couple of email addresses here that you can reach out to us on. And we do want to thank you for your time, and thank you very much.